Okay, so now the situation is the cord is taut. The whole thing, the whole system is moving down with the velocity of VD, because remember we calculated that in part 1. We were asked what's the velocity of the ring D, and the ring D is the mass center, and that's just going to be going down with that constant velocity because there's no forces that are changing it. And then what I'm showing here is the velocity of A relative to D, because in addition to the whole system moving down, A and B are rotating about that ring D, which is the mass center. So I'm showing those relative velocities. The velocity of A relative to D, and the velocity of B relative to D. But that's just going on while everything's moving down. Okay, but I'm going to use these ideas of the relative velocity and then the total velocity of the whole system, VD, to calculate the angular momentum about G, or D. I mean, it doesn't matter now if we call it G or D, right, because it's the same point. So that's what I'm doing here. I want to calculate the angular momentum at time 2, when the string is taut, about point G. So I'm going to sum up, well, if you look at the formula, there's an alternate formula. It looks like this. R cross MV plus HG, where HG is R cross the sum of R cross MV prime. Okay. There's bars on these. Okay, so, of course, okay, so this, instead of calculating the individual absolute angular momentums of each particle, like we did here at time 1, instead I'm going to use this alternate formula, which kind of, and this was, I think there was some homework problems where you verified this formula. Do you remember?
I do all the cross products for...
Yeah, it was really a tedious problem, but it basically took you through various steps and you calculated all these quantities.
It helped in the midterm.
Was it? I think you're right, I did put it on the midterm. So, okay, so this R bar, so this is the displacement vector from the mass center to wherever you're calculating the angular momentum about. Well, in this case, we're calculating it about the mass center, so this is going to be 0. So this term in this problem doesn't show up, but if we were calculating it around a different point, then you would have to account for this term. But, okay, and then plus the angular momentum about the mass center, which is all I'm doing. So that is just the sum of the angular momentums relative to the mass center. I don't know if you remember this prime. Basically, it's the velocity, it's the relative velocity. It's not an absolute velocity. It's the velocity relative to the mass center, which is exactly what I'm showing here. VB with respect to D, VA with respect to D. These are exactly what this prime indicates. This is hard stuff. You might have to go back and review. This, in my opinion, this is the hardest stuff of the whole semester. I know, I do too. Eunice said he hated it. But I've grown to love it. Okay, so I'm just plugging into the formula here. So so we've only got 2 particles. So let's do A first. So remember, this is L. So R is just L.
So which chapter is this one?
14. M, V, A with respect to D. And in this case, this is perpendicular, so the angle is 90. So that's why I'm not even showing the cosine of an angle, because cosine of 90 is 1. I mean, I don't know if you,
Can we use chapter for 15 to solve that problem?
no, not that, I don't think so. Okay, and then when you calculate it for B, you're gonna get the same thing.
You forgot the K hat.
Thank you. So it's just gonna be twice it, because VA with respect to D, the magnitudes are gonna be the same. So I'm using that idea. And now you just take this and equate it to this and solve for VA with respect to D, and you're done. This is, I think, the hardest problem in the whole course.
Is it VL, V, D?
It's
Same?
it's,
But the other
yeah, I'm
one
saying
is-
it's the same, yeah.
Same magnitude, but opposite.
Right.
But it's still the same.
Well, they're actually, well,
They're opposite.
no, I mean, in any
Yeah.
one instant,
Same magnitude.
they're the same magnitude in opposite directions, so there, you have me now? All right. Okay, let's,
I'm a bit confused about why you picked G. You have picked any other point besides G?
yes,
'Cause of
you
the-
could have. And in fact, it actually made me feel a little bit better to pick another point, but it made it more complicated.
It's the easiest solution.
But you could, in fact, I'd encourage you to go back and do this problem, picking D. And don't let D move. I mean, D, like what I'm saying is the original position of D. Take that as your original, as the point that you choose to calculate the angular momentum about.
Oh wait, that's not a good idea.
It makes it, it's a lot harder. The math is a lot harder, but it works out to be exactly the same.
Yeah, you have to find a position of A and B when the length is, when the displacement is exactly to M. And that's not easy.
I'm not quite sure I'm following what
You
you're
can
saying.
pick A.
Anyway, let's cut. Let's go on.